All right, let's start. So since you reminded me of 18 minutes, and these 2 minutes go away from your time, so I should probably. So let's start now. Hello, everyone. This is the HDF Town Hall session on the last day and the last slot of the ESIP summer meeting. I think what that gives us an advantage that I don't know if ESIP staff would agree, but we can continue because there's nothing, there's no other follow-up sessions. Today we have 5 speakers, and so as I already mentioned, there is about 18 minutes per each. I will give a gentle warning at about 16 minutes so that you roughly know, and then hopefully there'll be some time for questions. Anyone can post questions in the chat. My only suggestion is that we keep the discussions in the chat to a minimum. I personally find it distracting when I listen to the presentations and speakers that there is a parallel discussion going on in the chat, but if need be, we'll adjust, obviously. The only last one to those who are in Kiko chat and go to the Google Docs, there is a second page. There is a section called Community Wishlist for HDF. We are very interested to collect any suggestions from the participants for the future directions, and please add them throughout the session. And if time permits, we may actually revisit and just go and check them. But definitely, they're not going to get lost. We are going to preserve them after the meeting. And with that, our first speaker is Elena Purmal. She is one of the originals from the HDF group, and I think everyone knows her or heard of her. And that's pretty much it, Elena. Please take it from here.
Okay, thank you. And I have 15 minutes to talk about HDF software, its current status and future directions. So I will talk about releases, development efforts, and outreach. And here is the link, and I hope we'll also have the link in the chat room so you can go directly to our document to put your thoughts about what would you like to see from HDF. So very quickly about HDF releases. As we know, our group supports HDF5. It's not only supports, it develops, maintains, and supports HDF5, HDF4, and HDFU. It is libraries in HDFU Java-based browser. And you can always go to our website and you will find the release information, source code, and binaries for Linux, Mac OS, for Windows, and for many different variations. If you do not find what you need, please contact us. We also provide compression plugins, and about them a little bit further down. They also will provide binaries so you can use those with the releases we provide. Few words about HDF5. Currently, we support 3 major maintenance releases, 1.8, 1.10, and 1.12, and the latest are listed here. 1.10.8 and 1.8.23 are coming in fall in a few months, and you may ask why. In the past 6 years, we did a lot of development in HDF5 that slowly created performance gap between 1.8 and later releases. Some new features added performance overhead. We have applications that work with a lot of objects in HDF5 files were affected. And when I say a lot, it's tens of thousands. Usually NASA products do not have tens of thousands of objects in HDF5 file. We're well aware of the problem, and we are working toward removing this gap. And until we really make sure that 1.8 performs in reasonable threshold of 1.12, we're supporting 3 lines of releases. But as I said, not everyone can be affected. So stay tuned, you will see those improvements that are coming in new releases. What is also common for all releases starting with 1.10.7, which was last fall, we switch our compression, SZIP compression that we supported for many years, like for 15 years. SZIP compression that we support that comes with a restrictive license. You can not easily distribute data that SZIP compressed. Encoders can be licensed and not freely available. We replaced it with a new implementation that comes from Joint Climate Computing Center called AAC. It is also open source, but the difference is that it comes with BSD license, and there is no any restriction on using data that is compressed with this library. Both libraries are compatible, so you will not have any problem switching from one to another, and we distribute, we point from our website to a new distribution, and we also provide binaries using the new SZIP open source BSD license file. So we strongly encourage you to migrate all HDF5 based software from 1.8 to our latest, greatest releases, and you can go to even 1.12 if you do not see any noticeable performance drop. We put bug fixes, we add new features, and we also work on HDF5 common vulnerabilities and exposures, so-called CVE issues in all our maintenance releases. And usually the most of the issues applied to the latest releases. So don't be scared with those CVEs, but they're serious. So those CVEs are reported when someone intentionally corrupts HDF5 file, just going and modifying some bits and pieces of HDF5 file. And unfortunately, library in some cases doesn't behave and fail gracefully. It may not detect corruption, and it may just give you core dump. If you really worry about integrity of HDF5 file, you may do many different things like storing checksum on your file system and some other precautions. But really, to avoid the issues, we recommend that you use libraries in file format 110 and later, because for those version of file format, we provide checksums and we store checksums for HDF5 data, metadata in the file, so library detects easily if metadata becomes corrupted. Still with raw data, we have capability for a long time to store checksums for raw data, but of course it may slow down performance when you read raw data back. So it's up to you how to deal with integrity of HDF5 file, but we provide some mechanism to mitigate the issues. For HDF4, we still support, we don't do much development. The focus is on bringing HDF4 and support on the new systems, mostly on new Mac OS, and Big Sur will be releasing later this year. And HDF, our browser, the only change that was happened, we supported with OpenJDK. Right now, we still do not have HDF for the latest releases 1.12, and we are working on this, so it will coming. But right now, it's 1.10 based and 4.2.15 based. So let me talk quickly about our development efforts. And I will mention there are a lot of going on, but probably two of the most relevant things here. As you know, in HDF5, one can compress individual data arrays that go into HDF5 file, and different compression methods based on the data can be applied to individual array data, or even combination of those compressions can be applied. HDF5 comes with built-in gzip and szip, and as I mentioned, now we're using open source BSD license szip, but it also comes with support multiple lossless and lossy compression plugins via our plugin mechanism. Those compression plugins are registered with the HDF group. There is a page where you can see all registered plugins. But what we support is a subset of all registered plugins, and we support most popular compressions used by Python community, especially in H5Py and PyTables, BitShuffle compression and JPEG. And we also recently added support for ZFP and SZ compressions that were originated in HPC world. What is interesting about those compressions that they come with lossy and lossless, they are very fast. And now there is active development to moving those compression methods to GPUs. And as a result of this, we will be looking into enable GPU compressed features in HDF5. You can find plugin source in our GitHub repository. And as I mentioned, binaries are available too. We're very well aware about other compression libraries, plugins that are floating on internet. It comes from synchrotron community, and I think one of the is in Earth science community. So as long as all those filters have the same origin, you may use any of those repos to work with your data. They should be the same. Recently, we added a capability for parallel compression to compression to parallel libraries. So we now can not only read compressed data set, but while accessing HDF5 via parallel library, but also we can write. And currently we are looking into scalability for parallel applications that use compression. So stay tuned for more improvements in this area. Another big, really main focus, very big focus is what are the new ways of accessing HDF5 data? You probably heard, if you listen to TileDB talk, that file formats as they are now binary, they become obsolete. They still will be used, no question about it, but applications and new demand on science and computations, engineering require new type of storage. And we looking how to allow HDF5 applications to access data in object store, in cloud, or use node local storage, or how to reorganize data for optimal IO or use even different file format. And we are doing it with the new mechanisms that we added last year to HDF5 1.12 releases, the virtual object layer, which is a thin layer under HDF5 APIs. It captures HDF5 API calls and redirects calls into HDF5 wall connectors, or sometimes they're called wall plugins. And connector does all heavy lifting, putting data, for example, into DEOS object store, which stands for Distributed Asynchronous Object Store. We are supporting that plugin now. Or it can be go to, say, S3 using RESTful. We call our library now as native wall. And native wall have another mechanism how data can be reorganized in storage, but it will be reorganized in the HDF5 file using different HDF file drivers. And we recently released a splitter driver that maintains separate read and write only channels. So you can really mirror two files on the file system. And there is a mirror VFD that uses TCP IP sockets, or you can substitute easily any other protocol to perform write-only file operations on remote system. When you combine those two VFDs, you can have local copy of the file, stream file to remote system, and for example, on that remote system, other HDF5 application reads from the file and say does visualization or some analysis. Those were released, and currently we're working on two VFDs of interest. It is new single writer multiple reader that will implement full functionality for reader processes to access file modified by writer. Now writer will be able to modify file without any restrictions, and reader processes will see raw data and, more important, metadata at really real time. And another interesting development that will be released is Onion or Provenance VFD that stores multiple versions of HDF5 file within HDF5 file. HDF5 library will be able to discover how file was changed between open and closed calls, and you may have tools to replay different versions. So few words about outreach. If you need help, you know where to find us, Help HDF Group, or go to the forum. EOS help. Joe will answer your questions about HDF EOS products and software. We have a lot of documentation. And what is recently, we started HDF Clinic every Tuesday at 1 p.m. Just show up. If you have any questions, any topics to discuss, we'll be happy to see you. And in October, we'll have our 4th HDF users group meeting, and we're looking for the speakers. If you are interested to learn more what people in the world are doing with HDF or want to present your work, we encourage you to submit your talk. Submission is open right now. In the past year, we finished move to GitHub, all HDF software in GitHub. And more than that, HDF documentation, HDF5 documentation, we moved reference manual and some other topics to Doxygen. And there are links on this slide. You can go and see that documentation. And it became now, because it's served differently, it's now searchable, indexed by Google, much faster performing. So we're trying to address the question about our documentation, that it was slow and it was hard to find. And now you can contribute to both to software, to the code, and to documentation to help us to improve it. And I believe this is my last slide. So thank you. And I believe we have 2 minutes for the questions, or maybe not.
Excellent. Elena was really a team player. So yes, questions. I have one from Chris Linus. I will read it. It says, if a malicious actor has created a corrupted file in HDF5 1.8, what methods should people reading the file use to protect themselves?
There is really no way. I don't know how, what does it mean to protect? So first of all, move to the latest version of the library, because when we know kind of how file can be modified, we address those issues, and we modify the library to fail gracefully, not to crash on you. But really, it is open specification, it's open file. It's really not much we can do, except, as I said, I encourage people to move to latest file format, at least 110.
Thanks, Elena. Any more questions?
And of course, storing, checksums, whatever, on the system level protection is probably the best way right now for old files.
Thank you. Another reminder that we have this community wish list section on the Google Docs from KikoChat, so don't forget about that. And with that, we move to our second speaker. I only know him as JP. I don't even try to guess what his real name is. Apparently, it's very dangerous if you guess it and use it. So he'll be talking about H5 Coro, another interesting method to access HDF5 data in the cloud. And JP, take it from here.
Thank you. Yeah, my full name is Joseph Paul Anthony Swinsky. So that's why I shorten it just to JP.
Oh, now everyone knows. Ah, yes, yes. All right, all right. Thank you.
Okay. Let's see. Can you guys see that?
Yes, all good.
Okay. So yes, I'm going to talk about an effort called H5 Coro. It is the cloud optimized read-only library for reading HDF5. So first, just want to ask this question, throw it out there. Does HDF5 work well in the cloud right now? I guess before.
You want comments in the chat, or you people to?
Oh, I mean, you can throw it out. It was a hypothetical question, but yeah, okay. People can jump in for sure. Anytime people can jump in.
Then go for it. Continue. That's
okay. Right. Yeah. So I guess the first thing to ask is what I mean by cloud. And I'm just going to give my definition, or the definition that we're working with, knowing that it's certainly not the right definition, but it's a good working definition. And that is, for us, cloud means that the data is very high latency, but very high throughput. And compute is easily scaled. So when we think of cloud, at least in my group, these are the two main things that we're thinking of as far as the environment that we're operating in. And so when we think of HDF5 in that environment, I think it's safe to say that the H5 data format works just fine in the cloud. There's nothing, in our experience, there's nothing about the format that is has any issues with working in a cloud environment. The format is cloud ready. But the library, the C library that all of us use, it was not written for the cloud. It was not written for a high latency, high throughput environment where scaling, horizontally scaling is done very easily and dynamically. And that was just not the intentions of the library. So as a result, on the project I'm on, which is ISAT2's slide rules, the name of the project, it's a on-demand science data processing system that runs in AWS. We have undertaken the effort of writing an HDF5 reader from scratch in C++ that is optimized from the beginning for cloud environments. So what is the environment that we're running in? What are our constraints or assumptions that we can make? So for us, and this may not be true for you, it's certainly not true for everyone, but for us, the data that we're working with is static. So it's all science data products, most of which are NASA science data products. They were generated once and they will never change forever after that. And if there's a need to change them, a new version of the data is released and there's a whole different new set of files that we can read. So once a file is written, it stays that way forever. So we have kind of a write once, read many data set. All our data is time series, so it is sequentially stored in memory in time. And then we are accessing the data in S3. So as I mentioned, it's very costly. Every read suffers a upfront penalty, but once you get going, you can really fly. So given those, just at the highest level, what would we do? Like what would you do, right? Well, you minimize I/O, the number of I/O operations at all cost, even if you overread the data, right? So if you're paying a penalty for every read operation that you make, you minimize the number of reads because you know you're going to make up for it once you get going. So we do that, and the two main ways that we do that is through caching and through what's called a range get, which is just a HTTP get to S3 that provides a start and a stop location so that we're only reading portions of the objects in S3. So what does this module look like in our system? So I mentioned our system is called slide rule. When we started out, we were very conventional in our implementation. So we were linking in the slide rule application here was linking in the HDF5 library. It was using RESTfile as the connector, and it was talking to HSDS. And HSDS was talking to a metadata repository, which provides links or pointers into the H5 files stored in S3. And then it also would have direct access to the H5 files in S3 that we were interested in. And so we've taken that system and we've made a very small point solution and embedded it right in our application. So it is just a C++ module that links right into any running application. And it does not use a metadata repository, it just goes directly to the H5 files. So what are some of the key features that this library has? So to get performance, we've done these four things. The first is that all reads are concurrent. So from the very beginning, we wanted to have a multi-threaded model. So we want to be able to, if we're reading a 2 GB H5 file, we want to be able to spin up or already have a thread pool with 40 threads all running at the same time. And we just want to be able to fan that read out to those 40 threads and have them all hit S3 at the same time, completely concurrently. In the current HDF5 library, all reads are serialized. So even if you have an application that is multi-threaded, and even if you have a very robust parallel system like HSDS on the other side, if you're going through the HDF5 library per process, it is serialized. So this really does a couple things, but the biggest of it is it makes it easy to parallelize the code. So we're not, not spinning up multiple Docker containers, each with their own instance of the HDF5 library. Each read way down in the code can very easily spin up multiple concurrent reads. The second thing is that we are not bound to the individual chunks to do a read. So most of the HDF5 code currently works per chunk. And even some of the other efforts that I've seen where they are taking HDF5 and overlaying other indexes and kind of putting an overlay format on top for cloud access, they're still accessing the data per chunk. And that gets a little difficult because different chunk sizes are going to be optimal for different environments. So if you're reading the entire data set, well, then you want the biggest chunk size you can get. If you're reading a very small part of the data set, you want a very small chunk size. And because we're an on-demand system, we actually don't know. We're not a pipeline. So it's user-driven requests. We can't predict what the reads that the users are going to make. So we have all different types of reads, little subsets or entire data sets. And so there is not one chunk size that is optimal for us. But it turns out, and we've actually, this is true for a lot of the different ISAT2 data products that we're using. It's also true for other projects in which people have asked me to take a look at their data. It turns out because the science data, the way it's written is the writers all have the data available when they write the file, and it's like a one pass through. In all the data sets that I've seen for NASA science data, the data is right next to each other. So the chunks, there's high locality within the H5 file of the chunks themselves. And so there's no reason to, in that case, to just read one chunk and then move sequentially in memory and read the next chunk. And so there's heuristics in H5 Coro that make guesses, really. It can't know until it reads it, but it makes guesses as to the start and the stop of a region. And then it reads that entire block, and then it goes and parses through and pulls out all of the chunks. And if it misses some, it then goes and makes another guess and tries to read as much of it as it can. So it's constantly trying to minimize the number of individual reads. So if your request is a whole data set, well, it's going to try to predict what the beginning and end location of the B tree in memory, and you go down into at the bottom of the B tree, and you've got all the chunks at the bottom, and it's going to predict what the beginning and the memory address is of that, and in one read, it's going to try to read them all. Likewise, if you're just pulling out a little subset, it's going to try to spin down, figure out where that is. It actually predicts. It doesn't have to transverse, and it makes a guess at where it is, and then it corrects it as necessary. And that dramatically reduces the overhead of reading data. A lot of the ISAT2 data sets have tens of thousands of chunks, not hundreds of chunks, tens of thousands. To read one data set, you may be looking at reading 70, 80,000 different chunks. And to do it per chunk to S3, that's 70 to 80,000 individual TCP IP connections to S3 with first byte latencies on the order of like 60 milliseconds. So you just do the math and it's insurmountable at that point. And we can get those down to like 5 or 6. Third, the system is serverless. So it just links right in, so it scales naturally. It just makes it easier for design. And then lastly, we don't need a metadata repository. We traverse the file to build the necessary metadata. It turns out that we can read the beginning of the file fast enough, and we do cache those results, that is not a major contributor when you're reading a lot of data from H5 files. Now, if you had a ton of really small H5 files and you're reading just a few bytes from each, or a few kilobytes from each, then yeah, it would, to read a megabyte of metadata file, to read a few bytes from each file would not be good, and we need a different design. But for most of our cases, we have fairly large file, hundreds of megabytes plus, and to read a meg of metadata is just proportionally not significant. How am I doing on time, Alex? I forgot to look when I started. Oh, I can't hear you. Sorry.
Oh, yes. 12 minutes.
12 minutes. Okay, great.
12 minutes. Thanks for asking.
So, okay. So we did do some performance runs. For us, we have granules. The science data is divided up into granules. And so we did do some performance testing of the new system, reading a set of granules out of S3 from US West 2. So all of this is in US West 2. And I won't dwell on this too much, but it's a huge performance improvement. So it turns out, and this is the thing I want to say, is that if you write a targeted point solution for your application, when it comes to reading out of the cloud, you can get tremendous performance benefits. And so we have, an order of magnitude increase over HDF5 REST file. So the same data set that was taking about 2.5 hours to read using the REST file takes about 2 minutes reading with H5 Coro. And it's really on the order of an uncached read to a file system. So you can see on the line right above the highlighted line, just using HDF5 to the local file system. If it has to pull that file off of disk, it's about as long as it's taking for H5 Core to read uncached out of S3. And this is really just because we can with very few reads stream a whole lot of data. Now, for our typical use cases where we are subsetting, we see those going from about 1.5 hours down to 25 seconds. And all of this, so why is this such a huge improvement? It's because the data sets that we're using were being read per chunk, and the chunks were very small. And so we either would have had to re-chunk to the exact size that we wanted, or we do something like this. So for the rest of the time I have, I want to talk a little bit more about H5 Coro and just, I guess, promote an approach that I'm hoping to argue for. So this right here is the only API to the module. So it turned out, we have a server running in AWS. It scales. It does all sorts of stuff with the science data. It's doing all sorts of calculations and handling all sorts of API requests. And when we boiled down the interface to H5 that we needed, this was it. Like, the only thing that we needed to do for all of our H5 access was we needed to be able to read, what was the URL? So what's the bucket name and resource? What's the name of the data set? What's the type of the data? And if it's multidimensional, what column, and a start and stop row. And that was it. Now, certainly if your data is image data, this API would look a little bit different. But I guess the thing that I'm challenging people on is, if your system is primarily a consumer of science data, I wonder if the interface to the H5 data is not much more complex than this. Right? If it's image data, maybe it's a window, or you know, 3-dimensional would be a cube, right? Instead of here being a slice. Now, by identifying our interface to be this, really everything else follows from it. Because now we can say, oh, look, it really comes down to a single data set read. And we can parallelize all of those data set reads. And so if we're reading 40 data sets out of a file, well, we can read them all at the same time. And there should be almost no penalty for spinning that up. If you're going to the same data set, we do keep a same resource. We do keep a context structure, and that does some local caching so that each data set doesn't have to retraverse the metadata at the beginning of the file, or you know, it's sometimes in different locations in the file. And so we do save some there. But anyway, so this really was kind of the start at seeing that we could really optimize our reads to S3. And at the end of the day, though, regardless of what you do, there's going to be a slice of data that you need, a start and a stop. And as long as the data is sequential in memory, matching the semantic read of it, the processing read of it, then you're good to go. The only time this does break down is if when you go to read the slice of data, if the data is not stored sequentially in the file and it's separated sufficiently enough that you would need to issue separate reads. So I know there's a lot there, but this is really the crux of it. And this is why, you know, when people say, well, is H5 file, you know, is H5 good for the cloud? Well, it's like, well, at the end of the day, it doesn't matter if it's an H5 or ZAR or, you know, TileDB or whatever it is. You're going to have a read. It's going to be, for time series, it's going to be a slice. For an image, it's going to be a window. You know, for multidimensional, it's going to be a cube. And you just have to ask, is the physical correlation of that data, where it's local to itself, does that match to the physical location of the data as it's stored? Is it local to itself? And if yes, then you're going to have an efficient read. And if no, then you're not. And that's independent. There's nothing in the H5 format that is better or worse than any other format at that. So anyway, maybe if we can talk more about that if there's time at the end.
All right. Oh. Well, you're over now. So.
Oh, I am. Yeah. Oh. Okay. Yeah. So then we will. I must have done the math wrong on the time. Well, then I will stop here and open it up to questions.
Yes, there was one about, is it H5 core source code or binary available? And there was a link that Elena posted, but you are free to answer that one. And then any other question.
Oh yeah, yeah, perfect. Yep, that link is great. Thanks, Elena.
Any other questions for JP? All right. Let's see, go to the next speaker. Thanks, JP, a lot. It was a great talk, and I think you asked really, really important questions. John Reedy from HDF Group. Take it from here, John. Are you muted? I can't hear you.
Oh, sorry. You hear me now?
Yes.
Okay. And you see my desktop?
Yes.
Okay. All right. So welcome, everyone. I'm going to talk about recent efforts for serverless HDF using HSDS. Somewhat ironic, since HSDS stands for highly scalable data service. But as we'll see, there are some benefits to having a serverless approach. So we'll talk an overview of HSDS, the HSDS storage model, work we've done with AWS Lambda, and then finally, this direct access mode. So HSDS, it's a REST-based service for HDF data. And our criteria was to be highly performant, scalable, support features of the HDF library, and to be compatible with object storage or POSIX storage. This was originally developed under NASA Access 2015. So the architecture is like this. The service works as a set of containers. We have these blue containers, which are service nodes, green containers, which are data nodes, and a object store or POSIX store, where it's set up so that each data node owns a partition of the object store, a virtual partition. And when a request comes in from a client, it lands at any one of these service nodes. The service node has this capability to multiplex the requests across one or more data nodes. And this enables us to drive a fair bit of parallelism. So as JP was discussing, with, for example, S3 storage, it's high latency, but high throughput. So if you say need to read 100 chunks, if you can be reading multiple chunks per container at the same time, you'll get much better throughput than if you had to read those chunks serially. We support HSDS on a variety of platforms, Docker, Kubernetes, EKS, AKS, DCOS, and different storage systems, POSIX, S3, Azure Blob Storage, OpenIO, and Ceph. And the advantage, particularly for Kubernetes-based systems, is that you're not limited to the compute or network capacity of a single system. You can run the server across the cluster. So then you gain all the CPU and all the throughput of the nodes in that cluster. So before I talk about serverless, why a service? Well, it's nice in that if you need remote access to large data sets, it's much better to do the heavy lifting close to the data than bring all the data to your desktop and then extract the necessary bytes you want from that. Another benefit is to coordinate multiple reader-writer, right? So HSDS supports clients that can be both reading and writing to the same data objects at the same time. And in this scenario, HSDS serves as a coordination point, if you will, to make sure that, say, two writers don't overwrite each other's data. Another thing is a language-neutral interface to HDF. So in the modern world, REST APIs become kind of a standard interface, right? So it doesn't matter if your application is C or Java or Python. Many systems now are built to communicate across a REST API. But through Python or the RESTful, we provide HDF5 API compatibility. Another benefit is web-based applications. You can't directly use the HDF5 library, but through the REST API, it's easy enough to create web-based applications that are reading content from HDF5 files. And many modern systems are built to run across a set of containers using a microservices approach. And here, HSDS fits in very well. Next, briefly talk about the storage model. So in the HSDS storage model, it works much like with ZAR in that rather than an HDF5 file that contains different types of objects, we shard the contents so that each HDF object is stored as a JSON, and each chunk is stored as a binary object. The advantage of this is that we allow efficient updating of objects. So in object storage systems, to modify an object, you typically have to rewrite the entire object. Obviously, if your objects are beyond a certain size, they'll be very inefficient. So we limit the size of objects to, say, around 8 megabytes per object. Here's an example of what the sharded schema would look like. You have a root JSON object, and then each HDF object within that air quotes file will have an ID, a metadata JSON, and for data sets, you can have one or more chunk objects. So for example, object 3_ID has a dataset.json that stores the type and shape and so on. And then we have, any number of chunks where it's like 0_0_2 would be the second chunk in the first row of the last column of that dataset. Okay, so that's great. Let's talk about HDFs without service. So two approaches. We have AWS Lambda, where HDFs implemented as a Lambda function, and this direct access model. And the idea of these is to take advantage of all the capabilities of HDFs, but without having to set up a server. So again, the pros and cons of running a service. Having a service has an actor to mediate access to a storage system. So for example, you don't need to have credentials as a client to access a storage system if the service itself is mediating that for you. Service can cache recently accessed data, speed things up, minimizing data I/O between the client and the server, and synchronization point. So it's all well and good. So why is it not good to have a service? Well, maybe it's just too much hassle to set up and run service. It can be a challenge to scale the capacity of the service to the load of the clients. So even though HDFs is, as its name, highly scalable, it takes some effort to constantly change the capacity of the service to change the load from clients, especially if those client load is highly variable in itself. And then finally, if you have to have a server running 24/7, that's not a insignificant cost running on a cloud platform. So let's talk about AWS Lambda. AWS Lambda is a service that enables a function to be executed in this cloud context without the need to pre-set up any kind of infrastructure. Its cost is astounding 0.000000167 pennies per millisecond. Besides being its cost, it's the advantage of this infinite elasticity, meaning that with a cluster, obviously you can spin up some down number of servers, but that takes some number of minutes, right? With Lambda, you can go from no activity to 1,000 parallel functions instantly. And there's no infrastructure set up. There's no patching, no server backup, no monitoring. It's very reliable, low maintenance, et cetera. You can invoke Lambda through the management console, which I use a lot for debugging and testing, programmatically, or through this AWS service called API Gateway, which provides a REST API endpoint to Lambda functions. Challenges of Lambda. So if you have an existing application like HDFs, obviously you can't spend a lot of time initializing the application to run Lambda, because all that time is time the client is waiting for a response. There's no caching because each Lambda function runs in isolation from any previous invocation of that function. You're limited to a max of 6 vCPUs per function. And the runtime environment is restricted. So there's no Docker inside Lambda. You can't use TCP, and shared memory is not allowed. So I think these last two are restrictions AWS put in Lambda to prevent any kind of leakage from different customers invoking Lambda functions on the same environment. So our design for HDFS and Lambda is sort of like you imagine one of these like a fast food franchise where you build your restaurant, have one car go through a drive-through, and tear the restaurant down. Right? Not very efficient, but it works. So when the Lambda function is invoked, the SN node will be created and DN nodes will be created as subprocesses. And then rather than using TCP, we use Unix domain sockets to get around the TCP restriction. The payload is unpacked, and then the HTTP request is sent to the SN node. SN node talks to DN nodes read from S3, and the response is returned as a result. So in this way, we support the full REST API, but each invocation is run as a Lambda function. So here's a little walkthrough. So we start off, we have a payload, we have a HDFS image in the AWS container registry, and we have an S3 bucket. So first, the container image is loaded. We start our Lambda entry point. We unpack the payload. We spin up a bunch of subprocesses. We send a request to the SN. SN talks to DN nodes. DN nodes talk to S3. And finally, the response is packed into the result. There you go. So how does this work performance-wise? Well, the bad news is that in general, it'll be 2 to 100 times slower than the equivalent requests run on a HDFS server. So this is because it takes 2 to 4 seconds for the function to initialize, loading an image, spinning up the processes, and so on. And then there's no caching because it's everything comes and goes, and you're limited number of cores. But still cost effective. There's no setup, and you have the ability to parallelize workloads across 1,000 Lambda functions. So here's an example. Say we have a data set that is 10,000 by 1602 by 2976, so a data cube. And I want to do a hypersap selection for one column at a specific X and Y location, right? So in this big data cube, we're pulling out one skinny column of data. In this scenario, I would access 400 chunks, or roughly 1 gigabyte of data on S3. And from that 1 gigabyte, about 40 kilobytes is returned to user. Running this with HSDS and 4 nodes, we get 5 seconds of runtime, or roughly 204 megabytes per second of data processed. With Lambda, and I should say in Lambda, you can customize how much memory to dedicate to the Lambda function. With more memory, you get more virtual CPUs. So Lambda, a cold Lambda function, meaning that it hasn't been recently invoked, its runtime is 25 seconds, or 5 times longer, and a throughput of 40 megabytes per second. Once your Lambda function warms up, it goes down to 18.1 seconds. And then if we increase the amount of memory, so we have more vCPUs, the runtime goes down to 10.2 seconds, or 102 megabytes per second. So even the best case, it's still twice as slow as with a dedicated HDFS server, but remember the advantages, right? You don't need to set up a server. You don't need to pay 24/7 access costs to that. And I should say something else is, imagine, say, I want to do 100 XY points. So 100 XY points randomly located along this 2D area. I could run those 100 requests simultaneously, and there'd be no degradation in performance, meaning that 100 requests would take just as long as to run one request. So in that case, your performance would quickly pass what we get on a single HDFS server instance. Okay, so next we'll talk about HDFS direct access. So HDFS Direct Access is this idea to incorporate HDFS functionality without the need of a server. And it works by bringing the code close in to the server, much like we did with Lambda. And it's best used when your application is close to the storage, i.e. running on the same AWS region as the storage. And we support POSIX, S3, or Azure Blob Storage. So much like with Lambda, what we do is we run the SN code as a subprocess, the encodes as more subprocesses, and we communicate across these using Unix domain sockets. So when the file opens, we spin up these subprocesses, do whatever interaction with the file, and then on file close, we shut down the processes. This is enabled through the Python h5pyd package when the endpoint is specified as local. And all other functionality works just the same as if you had an HDFS server. So here's what it looks like. Again, we have the application talking h5pyd. h5pyd talks to an SN. SN talks to a bunch of DN guys. And these DN guys are talking to S3. So the advantage here is, say, compared to, as JP was talking about with the H5 library, is again, you are enabling this parallel access to the storage, right? So the more parallel threads you have to storage, the faster your performance will be. So the considerations here are that you're limited to whatever CPUs you have in your host computer. So no clustering. And you'll want to be close to data to minimize the latency and throughput of accessing S3. There's no, you'll need authorization, obviously, to talk to the storage system. So unlike with HSDS, you can have a client who doesn't have access to the storage bucket talking HSDS, and HDFS mediates that access rights to storage. Another concern is that you're running multiple clients. There's no provision for preventing those clients from overriding each other's talking to the storage. But there's no danger of the storage being corrupted. At worst, you'll be overriding certain data. The same approach could be used with the REST vol. To have a vol plugin that instantiates locally subprocesses, these subprocesses talk to the storage system, and you get the same kind of API we have now with the REST vol. So in terms of release, the Lambda is available now in the 0.70 beta release on GitHub. And obviously, this only works for AWS. Azure has a similar function invocation, but it's different in the details. So it takes some effort to create a similar capacity for Azure. We should have the 0.7 release out this summer. The direct access will be available in H5pyd version 0.8. Again, the beta is available now. And I welcome feedback in terms of GitHub issues, pull requests, email, forum posts, etc. Here are some links to the various pieces. And that is it for me. I'm actually ahead of time, I think.
No, it's 19 minutes, but who cares? Who counts? But who counts?
All right.
Thanks, John. We have one question in the chat from Rob. I'll read it. Could the benefits of parallelism in the serverless approach be hindered by the use of multiple sub-processes for the server nodes and data nodes in a regime of limited memory?
Yes. So there is some tuning you can do, though, right? So I find that basically you won't get better performance than the number of cores on your system. So HSDS works in such a way that in each node, it uses Python async to do multiple requests, right? So you're not limited to one S3 request per node. each node can do, I think it's like 40 or so concurrent S3 requests. So as long as you limit the number of sub-processes to number of cores, and you have each sub-process taking so much memory, but you can tune the amount of memory as well in terms of memory is devoted to caching and so on.
All right, any other questions or follow-on questions? No? Okay. All right, so thanks, John. Next speaker is Alan Johnson from MathWorks. And I will stop talking. So we are already running a bit late. So Alan, please start.
Sure, thank you. Can you guys, hold on, as it loads, see my screen?
Yes.
Awesome, thank you. So I want to thank the HDF group for inviting me. I haven't spoken at an HDF Town Hall at ESIP for a couple of years now. So this time I have some good news to deliver. Okay, so I am a senior software engineer at MathWorks. I work on the MATLAB team that does all the I/O for audio, video, image, and scientific file formats. And I've been here since 2013. And what I'm going to do today is I gave a very similar talk at the European HDF5 users group a couple of weeks ago. This has more info in it and is more geared to Earth and climate science folks. So I'll give an overview of our scientific data capabilities and our HDF interface. I'm going to talk about what we've been doing for the past few years and what we have new in 21B. I'll show a demo, talk about performance and compatibility considerations and future work. And I just want to make a note that anything I talk about in today's talk specific to 21B are available to MATLAB users now in the 21B pre-release. The full release will not be coming out until September, but you can try all our new stuff in the 21B pre-release now. So for MATLAB and scientific data, we support throughout both core-based MATLAB and the toolboxes like image processing toolbox and mapping toolbox, a whole variety of scientific formats. And our team mostly, well, it covers actually everything in the first section. So we work on HDF5 net CDF, HDF4 FITS CDF, the band interleaved format, and all the image formats except for high dynamic range, which is an IPT. We have our friends in IPT and our friends in mapping toolbox who have these capabilities, but I'm not so much going to talk about that today. It's going to focus on HDF5. So as a reminder, MATLAB has two HDF5 interfaces. We have the high level interface, which is meant for users to have real nice experience and ease of use, because as you know, with HDF5, the library itself can get kind of complicated. But for folks who are familiar with the C API, we have our low-level interface, which wraps the C API, gives a lot more control to folks. And what we have here is, this is a screenshot of a MATLAB live script, just showing a very simple example for high-level and low-level interface. And remove this. Okay, sorry. Are you guys seeing yourselves here, by the way? No? You guys can see the full screen?
Yeah, we're seeing full screen.
Oh, good. Okay. Mm-hmm. So on the right-hand side, this is our interface for high level and low level. The low level is just a sampling. We have over 300 functions, most of which we map most of the HDF5 functions in MATLAB. Oops, sorry about that. So here's what I'm going to talk about what we've been up to, because the first talk at ESIP I gave, I was all excited because we had just upgraded to 1.8.12 and we added support for reading data sets that were compressed using dynamically loaded filters. Sometimes I call them DLF. If you hear me say DLF, I mean dynamically loaded filters. Then what we did, a few years went by, and around 2019, we attempted to upgrade to 110.2, which was a new thing. 110 was stable now. We wanted to do it. What we had, though, was we saw major performance regressions in another use case at MathWorks for HDF5 files, and that's MAT files. So hopefully you know what MATLAB MAT files are. And version 7.3 are based directly on HDF5. They use the same library that our team uses. And they have a very specific use case that they want to store thousands and thousands of really tiny data sets. And that's the use case where we saw the most regressions. So our customers in our team are mostly the earth science and other domains that use HDF5 companies. And they don't have that use case so much. It's more large multi-dimensional data sets. But we still had a problem because we didn't want to break all the MAT file folks. So we attempted the upgrade, performance regressions, and then I don't want to spoil this, in the meantime, in 20B, we added support for remote data access for HDF5 data stored, both read-write on S3, Azure, and Hadoop distributed file system. And we wrote our own in-house virtual file driver based on the HDF5 Sec2 driver and combined that with the MATLAB architecture that enables us to read and write into remote locations, and did some magic with that. And that's how we were able to do this. And this works since 20B for all of our high level and low level functions. And then more time went by. And then the MathFile team also, because they use the same version of HDF5 that we do up until what I'm going to talk about next, they added remote save and load for MathFile 7.3. So then more time went by, HDF5 moved to 110.7 on the 110 branch, and we still saw regressions, but we devised a solution. So what I'm happy to say now in 21B, that the customer facing HDF5 interface now uses 110.7. Yay. We have new functions in our low-level interface for swimmer virtual data set, some for, not all, but some for fine-tuning the metadata cache, and the two functions for controlling partial edge chunk. We've also modified existing functions for 1.10.7 that were needed, like the new H5P set layout for virtual data set, the new option in H5F open for start swimmer, for the swimmer write mode. Also the H5P get and set libver bounds. Now, what we're doing, what we were able to do in order to make this happen is we symbol versioned with some magic, and only on Linux. This only applied to Linux, this caveat that I'm about to say. We symbol versioned both our shipping HDF5 libraries. So we're shipping two libraries. It's an interim only solution. We're shipping a symbol version 110.7. Again, this is Linux, symbol version 1.8.12. The 1.8.12 is still needed for the MathFile folks to avoid the regressions. And we've been working really closely, thank you to the HDF group and to other teams at MathWorks on a long-term solution for this, because we know we don't want to be here and any longer than we have to. Okay, so, I think I missed a thing. Here's our goal: ship one version and to stay current, one version of HDF5, and stay current with the HDF5 releases. So that is definitely our plan now, so we don't get so far behind. So here's some functional details in 21B. So we added about 30 new functions across our 16 APIs that mirror the HDF5 APIs, provide really fine-grained control for the features that I mentioned. We modified the existing functions that needed to be modified to work with 110.7. And of note here is because the work that we did in 20B is H5 read, H5 disp, and H5 info, which are all access or all reader type functions, can access virtual data sets hosted on S3, Azure, or Hadoop. So that's a really cool thing that we have now. So what I'm going, here's the slide that I know there's a lot of info here. I don't expect you guys to go through it, memorize it, but this shows that our functions, which as you'll see, they're basically pass-throughs to the HDF5C library, mapped to the HDF5 feature in 110. You'll see that fine-tuning the metadata cache, there's more. We didn't implement all of them. We're going to take a watch and wait approach to hear what customers say about that. So I'm going to start this demo. I want to explain what's going on. Probably I'll run through it once and then explain what's going on here. So just the big picture of what's going on. We have two virtual data sets that are going to be displayed. And one is going to be working with a mix of source and VDS files, local and remote. And then the right-hand side of the screen, we're going to be showing a swimmer and VDS workflow together. So let me just run through this whole thing. And it's easier if I explain it after it runs. But the right-hand side is bathymetry data that was stored as HDF5 files on S3. On the right-hand side is, and there's a virtual data set on the right. The right-hand side is both swimmer and VDS together, overlaying a physics model that is simulating like something huge, like a meteor dropped in the ocean. Okay, and I want to give credit to my awesome colleague Cedric Juanes. He's a physicist / engineer who came up with this model, and this is really great. So what I want to show here is on the right. That's what Cedric did was he took bathymetry data, that's public data, and that's stored in GeoTIFF format, and he's writing all those to S3 as 8 different HDF5 files. Okay. So, and then he's got the display here going on, the reader, on a local file system. And on the left-hand side, he's simulating 3 ocean sensors and writing to each of those as one writer, writing to an HDF5 file. And there's 4 MATLAB processes going on here. This is the main MATLAB process that's doing both reading and writing. And he's using MATLAB Parallel Pool to launch other MATLAB instances in parallel for the writing. And then we have each one of these files has 2 readers, one to read and display the 2-dimensional data sets for the source files, and the other one to integrate the VDS on top of the existing bathymetry data. And he made this disjoint on purpose so that we can show that the fill value is a little hard to see on top of the bathymetry data, but if you see at the bottom, there's the 2D representations, and the physics model on top, it shows this part here, which is the fill value to, that is because the data sets are disjoint. And when it all comes together, I'm gonna see if I can replay this again. Oh, shoot. Okay, sorry about this. Let's get to see this again. If I play this together, it's really nice because it shows how VDS is just great because it shows how cleanly, and of course, oh, here it goes. Shows how nice and seamless the model, the physics model on top of it is. Okay. So we were really excited to test this out. We did a lot of testing for swimmer and VDS, a lot of testing on the remote and local file systems. And we intentionally are not showing anything to do with swimmer on the remote file systems because of the POSIX compliant issue in the local file, in the remote file systems. So let me move on. Okay, so for performance, we did performance benchmarks for on 1.8.12 versus 1.10.7 for our functions. And we saw improvements with a whole bunch of them, H5 write, H5 create, a whole bunch of the low-level functions. We did see regressions with H5 info, especially with files that have highly nested groups, really, really small data sets in them. I'm working with the HDF group right now to figure out if that's the same issue as the map file folks were seeing. In the meantime, we do know we have work that we can do to H5 info. It's like a wrapper on top of a wrapper to make that more performant. So we're going to be looking at that next. And future for besides that, for more performance work in the future, we know that there's room to optimize our whole HDF5 code base. We have target areas that we have in mind. We definitely want to add more workflow-based performance tests. So for compatibility, so for our Linux users out there, and again, this is interim only, there was only one caveat, and that is folks who use filter plugins. And what they need to do, if they have any filter plugins with a call to the core HDF5 library, so I don't mean the H5PLX term, I mean anything like H5T create or something, because I know some of the plugins do. If they have a call to the core HDF5 library in the plugin, they'll need, in order for it to work, they'll need to rebuild with our shipping symbol version to 1.10.7. That will avoid symbol collisions. Again, interim solution only, and we're going to provide two options for them that they can rebuild their plugin with our shipping symbol version 1.10.7, or we'll publish our new export map that we use in order to create the symbols that are used in the library, publish that on File Exchange, and then users will build their own HDF5 version with that, and then build the filter plugin with that new plugin. Again, we don't want to be here. It was either this or not have a nice upgrade with Swimmer and VDS. So again, interim solution. And also just another note about compatibility that most of you know is the set libver bounds is anything that was created in the new version of 21B, anything that you create and you set the bounds to latest and latest for the library versions to create objects, the files won't be compatible with earlier versions of MATLAB. And for future work, again, I can't say it enough. We want to ship one version, but we also want to stay current with the HDF library. That's really important to us moving forward. We want to support, we've been able to read data sets with DLF since 15A. What we're going to do next is, in fact, it's on my plate next, to support writing data sets using dynamically loaded filters. We want, in general, a better experience for our users to work with the filter plugins. I myself have worked with them a lot, and I find it a little bit difficult to use. And upgrade to HDF5 1.14 when that becomes available. We're going to take a watch and wait approach to our high-level interface for creating virtual data sets. It can, like I said, it can access them already, whether local or on the cloud, and maybe some swimmer controls in the high-level interface based on community feedback. We'll wait to hear from customers about page buffering, file space management, and any other feature in 1.10. And we're hoping to hear from all of you. So this is just the wrap up. So I talked about how we're now current with the new with HDF5 1.10 branch. We have the new Swimmer VDS and the caveat with the Linux filter plugin compatibility issue. And we really, really want people to try out our pre-release and provide us feedback. There's my email address. Happy to hear any wish lists, and especially with any questions, just reach out to me directly. And that was it. Thank you so much.
Thanks, Ellen. Any questions? Okay. No, so thanks again, Ellen. And Jolie, please take over, and we will go a little over 5 p.m. Eastern time, but this is all fun and you enjoyed it, so you why stop at 5? So let's finish it. All right, Joe, go for it.
Good afternoon, everyone. This is Joe Lee from the HDF group. And I'm a software engineer who maintains the HDF.US.org website. And although I have many other duties in my company, I enjoy maintaining the HDF.US.org website most because I can interact with NASA Earth data users directly. Thus, I've been maintaining the website for last 15 years. And it was the most rewarding experience in my life because I've received so many thank you messages from the website users. Today, I'll share my experience with the users of HDF.US.org website. And at the end of my talk, I hope that you can understand the basic data needs of Earth scientists better. If you work for NASA DAX, I hope my talk can help you improve your data services like NASA Giovanni and Harmony. I'm presenting this talk today because I believe that understanding humans are as important as understanding data. Before we talk about the users, let me explain what the hdfus.org website is. HDFUS means Hierarchical Data Format, Earth Observing System. We maintain the website to lower the barriers of accessing NASA Earth data in HDF. According to Google Analytics, we have about 100 unique users per day. However, if I check the raw web logs, I can see about 1,500 entries per day. The difference is due to the bots and some web pages that do not have Google tracking scripts, like code and sample data. And to reduce the email traffic and share knowledge more efficiently with the public, we have a forum. So far, we have about 1,830 forum users. And we get about 1 to 3 emails per week related to our website. Although we have some users, most of them are really silent. For example, our forum doesn't require registration for viewing all the contents. Yet people register forums, but they don't post anything right away. Our YouTube channel has about 7-8 subscribers, but there are not many comments. It seems that users prefer privacy more than public space, so they always send emails. So email is still the communication channel for us. Based on the questions that I received by email and forum, there are 3 types of users, and I call them locator, merger, and converter. And they are not mutually exclusive. One user can show all 3 traits of 3 types, and supporting such user is the most demanding, yet most rewarding for me. Here are some common questions that locator type user asks. First, I can find an example for an HDF file that I downloaded. Can you provide an example of the HDF file that I downloaded? And how can I find the let long data set within an HDF5 file or HDF4? And how can I filter my data using a feature mask? A feature mask is typically another data set within the same file that has feature like cloud, coverage, or uncertainty information. How can I subset data over a specific region, like India or China, using let long boundary or shapefile over my city in India? The shapefile can be country level or city or county level boundary. The merge type users asks how to combine data or multiple files. So they want to combine several bands in data sets together to create an RGB image. Sometimes they want to tile or mosaic multiple files, and files are spread over the regions of their interest. So big countries like Russia, China, India, their regions are split into multiple files in HDF files, and people want to merge them together. Converters typically ask the following questions. For example, how can I reproject or resample data? For example, source grid is very common. And how can I convert HDF to 4 different formats like GeoTIFF? I've seen a user who wants to convert to NetCDF3, removing all the groups in NetCDF4. In the other extreme, an advanced user asks how to convert HDF5 to NCJAR, then NetCDF can read. And some users ask how to I convert into CSV or plain text files. And the last question is, how can I open HDF with software that I'm using? For example, HDF to hack a geotip converter called the hack fails to convert certain NASA data products. And our users ask, our GDAR fails to read my HDF4 data. How can I open it? And some NCL users complain that I cannot open some NASA data sets. So our website tried to keep evolving, and we could evolve thanks to the continuing support from NASA EAD to contract. For example, we've updated the FAQ pages to explain why some HDF products from European Space Agency or JAXA will not show up. And MATLAB and IDEA examples, we have improved their APIs in retrieving lat-long information. In the old days, we used to rely on an external application called HDF US2 dumper to retrieve lat-long, which is no longer necessary because MATLAB and IDEA both improved their APIs to return lat-long directly. Python examples that we have parse the strong metadata in HDF EOS. And the strong metadata has the key geolocation information. And we use this high projection library to calculate lat-long from those strong metadata. If a data product points to another data product that has lat-long, and then we put them together on our website, so users can easily collocate what files they should download together for identifying geolocation. Finally, subsetting examples using lat-long boundary or shapefiles are directly available in FAQ pages. When it comes to merging bands and producing a pseudo color image like geotip, JPEG, or PNG, geospatial data abstraction library is very useful. Therefore, we enhanced the GDA example page with a new tool called the GDA MDIM Translate. This tool can help users to subset the right band because the dimensional order for a specific band can be quite arbitrary in HDF EOS. Second, Python and MATLAB are the two most popular languages for our users. And they keep asking how I can merge sinusoidal projection grids or source files together. Therefore, we created them for a few products, and they can be applied to other products as well. And as the interest in machine learning grows, the ability to handle a large amount of files at scale in cloud is very important. Therefore, we added an Apache Drill example that can query a collection of HDF5 files on object storage. And we worked closely with the Apache Drill team to test their fixes in supporting HDF5. Again, typical imaging-based machine learning always requires the standardized input on 2D grid. Therefore, we added Python resample reproject examples. Second, although GDA and HAG can convert many HDF products, users want to save data in GeoDip directly from scripting languages like Python and MATLAB. So we added those examples as well. And for merging data along time dimension, users want to save it in NetCDF. Therefore, we provided such example in MATLAB. And CSV, comma separated value, like a Python language, is quite universal across all domains and platforms. And many users ask, how to convert HDF to simple CSV that has a let long for every data point. So we provide Python examples to CSV. And there's a tool called the NCO, HDF operator, which is another great command line interface tool like a JITA for manipulating HDF files. So we keep updating it for common tasks like merging data along time dimension and editing metadata. So in the future, we expect the growth in user community in the following 3 types. The first type is artificial intelligence and machine learning user. For example, they will ask how to create a good image from HDF that can feed vision-based machine learning algorithms. For advanced users, they may want to train and test ML algorithm directly from HDF as inputs and even save their models and outputs in HDF for long-term archive. The second type of user will be big data user. As the amount of NASA HDF US collection grows rapidly, year after year, users will ask how to process them all in parallel distributed manner. Users who are not familiar with the supercomputers and MPI, messaging passing interface, they look for interoperable big data solutions like DASK or Apache Spark. And the third type of the user will be cloud. And as more NASA Earth data eventually will migrate to the cloud, they will ask how to run HPC clusters on cloud and process the massive amount of the HDF data as quickly as possible using MPI, given their cloud budget. For users who are not familiar with operating HPC clusters, they will ask how to convert them to query a large amount of data using the existing solutions the cloud vendors can provide immediately. For example, AWS SageMaker or Google AutoML and Azure machine learning pipelines. So finally, although we're not certain what future of data science will look like, but I'm sure there's one certain thing. No matter how smart AI or machine learning systems will become, our scientists are still important because they are the ones who can feed the data to the intelligent machines. HDFUS.org website will continue to help our scientists to locate, merge, and convert Earth data in HDF so that they can do their research, because their research can save human race on Earth from potential global disasters. And thanks for listening and have a nice weekend.
Thank you, Joe. Any questions for Joe? I just want to say that if you're HDFUS data user, HDFUS website is really a tremendous resource. And so you'll find many answers on it in their forums or with examples. And everyone likes examples. So if there are no more questions, the last call for any question to any of the speakers before we wrap up. We're already 5 minutes after. So if you want to ask a question, go ahead quickly, and then we'll close the session. All right. Well, it's a Friday, and for us on the East Coast, weekend has just begun. You on the other time zones, you have to work a little bit more. And so thank you very much for attending. We will capture the questions, and I'm right now saving the chat so we can add it to our meeting notes. And thank you very much. Have a great rest of the summer, and please consider participating in the HDF user meetings, especially the one in October. And thank you very much. Thank you very much to our speakers. Take care, everyone.